All right, good morning. My name is Greg Wadley with CTC and Associates. I'm the Clear Roads Administrator. We're all here for the final project webinar for the project entitled Determining the Migration of Chloride-Based Deicers through Different Soil Types. This research effort was led by Xiaoming Shi, who's on with us here today. This webinar is being recorded and will be posted on the Clear Roads website later this week for viewing by you and your colleagues at your convenience. I also ask that unless you're speaking, please remain off camera and keep your microphone on mute. However, if you have any questions or comments, please don't hesitate to enter them into the chat box and we'll address them at the end of the presentation. So with that, I'm going to turn it over to you, Xiaoming. It's all yours.
Thank you so much, Greg. Good morning, everyone. Again, this is the final presentation for the project Clear Roads CR21-07, determining the migration of chloride-based deicers through different soil types. And my name is Xiaoming Shi. Used to be a professor at Washington State University. That's when the work was done. And this is a project mostly in collaboration with the folks listed here. Dr. Taiwo Akinle is the one doing most of the heavy lifting in the lab and just graduated with a PhD from WSU. And then also other folks who helped the project include Dr. Max Fleury, Dr. Tim Game, and Mr. Paul Braun. So just to go to the backdrop of the project, why are we doing this? First of all, roadside soils are pathways and reservoirs for salt ions from those products used for snow and ice control on the roadways during winter road maintenance operations. These are typically chloride-based salts, such as sodium chloride, chloride, calcium chloride, usually sometimes blended with corrosion inhibitors. These salt ions may undergo different transformation within the soil and or affect the soil properties through various symptoms, such as the ones shown here in the photo. Basically, these mechanisms could be chemical, physical, or hydrological. And, one of those things, especially concerning actually, is the mobilization of heavy metals within the soil through ion exchange and formation of chloride complexes and the colloidal transport. So the interaction between the chloride salt ions and the soil particles can be very complex. So to gain a better understanding, we have to start from somewhere. There's so many different factors that could affect the transport behavior of these. Or as you can see in this figure, it illustrates how the roadways deicers tend to get into the adjacent environment, such as soil and water bodies through various pathways. But when it comes to how these deicer products or constituents migrate through roadside soil, the factors can include soil type and texture, geographic location, especially when it comes to variations such as humidity and temperature. All these factors could affect how they migrate or how fast they migrate. Like I mentioned earlier, there are many different ways for deicers to get into adjacent environment. This is only a piece of the puzzle. So for this project is trying to focus on understanding migration of chloride-based deicers in roadside soil. Again, if we look at the influential factors, we can group them in three buckets. The first one is the soil's own properties. In terms of physical properties in the first group, such as density, porosity, permeability, particle and pore size distribution, water content, organic or inorganic soil fraction, organic versus inorganic soil fraction. And the chemical properties of the soil is a second group, where we're talking about mineralogy, the chemical composition, the cation exchange capacity, the pH value, and so on. And the last group is the properties of the deicer itself. These could be concentrations, the ion valency, or the viscosity of deicers, Now, when it comes to different types of soil, we know from cumulative studies in the published domain that the coarser grained soil, of course, tends to facilitate the migration faster, and the fine grained soil basically gives less room for migration, and therefore the migration is slower. And typically, we're concerned about a zone which is roughly 30 meters from the sides of the road pavement and as far as 110 meters deep. That's a pretty large range. And of course, as it's further away from the location where the deicer was applied, the concentration could be much lower because of dilution by rain, snow melt, and so on. And also along the way, soil and vegetation could dilute them or slow them down. So the goal of this project is to provide winter road maintenance teams with a thorough understanding of how sodium chloride and magnesium chloride migrate through different soil textures and how agro-based inhibitors affect the process. So at the end, we expect to produce one-page fact sheets based on the results of a controlled testing program that would assist agencies in developing localized maintenance treatment plans. So to be more specific, again, we look at this case study back in 2009 by Samantha and Eric on the right. You can see the x-axis is the distance from the applied location or the pavement, and the y-axis is the depths inside the soil. So you can see the wider it is, the higher the concentration. So really the most affected zone is relatively small, right? Within almost 5 meters away from the road. But when you go a little further, let's say 8 meters, you still see some chloride concentration as high as, let's see, probably 200, 300 milligram per liter. So the vast majority of the zones where you see the dark blue is basically zero chloride. So that's the good news. But you can also see that it can go as deep as 3.2 meters and as far as 16 feet from the road. And if we consider, 300 milligram per liter is significant concentration. So that's kind of the zone. Of course, this is just one of the case studies reported. So in this project, we look at a few objectives. First, we want to evaluate the underlying mechanism for the transport of chloride anions, which is the negative charge ions, and also the different cations, which are positive charges, such as sodium and magnesium in roadside soils. In other words, when we apply a deicer, once they meet water, they actually dissolve and turn into different ions. So it's no longer just moving in one compound. So the second objective is to evaluate the effect of agro-based additives or corrosion inhibitors for deicers in the transport of such chloride salt ions in the roadside soil. So to begin with, of course, we did a comprehensive literature review, look at the past decades of research, and that's part of the final report. And then the task two was really to understand the current practices. So we conducted a nationwide survey. We obtained 21 valid responses as shown here in the map. And then out of the 21, we had 16 state DOTs. In other words, others were more municipalities. So according to the survey results, we found that we asked people, what kind of deicers they apply for various strategies of winter road maintenance operations, such as pre-wetting, de-icing, and anti-icing. As you can see in the chart on the left, few agencies actually use calcium chloride. Most common products used are sodium or magnesium chloride. And then we also asked the question about what kind of corrosion inhibitor they use. And out of the 21 valid responses, beet juice is the most commonly used additive to reduce the corrosion of such roadway deicers. And we also asked about dosage. You can see on the right-hand side, typically the beet juice dosage is around 20%. In other words, it's a 20 to 80 volume blend with salt brine. salt brine typically at 23% sodium chloride or 30% magnesium chloride. So here's a list of experimental methods. I'm not sure, Taiwo, are you already online? Can you take from this or?
Yes, he's online.
Yes, I'm online.
Okay, I can flip. Just tell me, go next page, then I can, yeah.
Okay. So this is a list of some of the experiments which we try to use in our study, and the list goes on. More specifically is the soil column experiment. That's represent like the prototype conditions on the field. And so in order to do that, we needed to just do basic soil classifications, such as particle size distribution of the soil, in order to meet the same soil type which we obtained from literature review, which is from the survey result. So you can move to the next one. So these are just some of the methods that we use. For example, this device is an XRF device for measuring the cations in the soil, so sodium and magnesium ions. And some of the methods which we use to evaluate our results, like the suction isotherms, like Fredlum and Longmire, are some of those. And these are just showing some of those methods that we used for this experiment. Next slide. Yes, so to carry out our experiment, we actually did two variations of soil column. One is to run our solute, our salt brine, in the vertical orientation, which is a vertical soil column. And then we also try to use the horizontal orientation, which is the horizontal soil column. And the basic difference between that is just to see the effect of gravity assistance on the flow of these ions through the soil, and try to see if we have changes in the flow properties and how the cations and anions interact with this soil when we try to change the orientation. And this is just quite representative of what happens in the field soil or in roadside soils, where you have Deicers migrating both vertically and horizontally throughout the soil. So next slide. And also to do this experiment, we try to mimic what we think will be the ideal concentration in the field. And so we try to start from the basic concentration that we got from our literature review, which is 23% for sodium chloride and 30% for magnesium chloride. But then after several trials in the lab, we saw that these concentrations are very high, and it's going to be very difficult in the experiment. And so we said, let's work with other dilutions that we think is possible based on literature review as representative of what happens on the roadway after snow melt or precipitation actions. So we work with two dilution, which is just 1 to 30 dilution for each of those brine, and 1 to 90 dilution. Not to also forget that we added 20% of beet juice and did the dilution accordingly. So 1 to 30 and then 1 to 90, just to see the effect of concentration ranges on the effect of these cations and anions in the roadside soil. Also, we try to use our machine learning methods to predict our results and try to go from experiment to modeling approach and try to predict further away from or extend the limitation of our data to see what we get if, for example, we apply these deicers in for a very long time. So you remember our experiment is finite, which is limited, and then we wanted to see if we can project other results. And that was the main reason for using our machine learning prediction approach, just to predict our lab data and see if we can get further predictions.
Actually,
and some of the
Taiwo, could you also mention the number of data points we would have to experimentally obtain if we didn't use machine learning, and how many we actually I mean, basically how, from hundreds to thousands, or actually we scale back from thousands to hundreds. Could you mention roughly?
For this experiment, if we didn't have to use machine learning, we're meant to get over 1,500 data points, which is just each of those data points means an experiment. So 1,500 experiment for each of that. And that's just basically the cation and anion. For all of the other experiments, if you want to check every conditions, you have to replicate those multiple times. So this is going to take several years to complete, actually, a very long range data result for this kind of experiment. And that's one of the reasons why we try to look into machine learning prediction to see if we can, one, basically design our experiments statistically to satisfy the final output, and then use our machine learning method to project further results after from where we stopped from our experimental data collection.
So we were able to do it with what, 400 measurements?
Yeah,
Roughly?
probably about 350 thereabout, the point. But that's after so many considerations, and we had to cut down on so many of the data points. But then basically, we still maintain the same input variables for this machine learning prediction, which is just making sure concentration, sodium, magnesium, and chloride are well represented in our model. And using different variables, we chose the chloride salt concentration, and then beet juice, and then look at the dilution ratio, and also the pore volume. And then the two-stage modeling, which is just classifying from zero to non-zeros, that's using the statistical methods, and then using regression analysis to be able to predict our results. So for example, we talked about the data set, horizontal soil column 172, a training data set and validation set. And then also for vertical, we had almost similar 186. So it's about close to 400 data points for this model. So if we go to the results, one thing we try to do, because now is a control experiment, which is basically trying to get the results which we obtained from the literature survey that we sent out to the DOTs. And so in the lab, we had to make a mix of soil to have the same properties as those roadside soils. So for example, we had about 7.46% of clay in our soil sample, silt was about 40%, and sand 52%. And so getting this mix, we're able to replicate our sandy loam soil, which is typically obtained in the roadside soils as expressed in our survey results. These are just basic classifications. So getting the compaction results for the lab, which is a representation of what happens in the field. So compacting to similar densities as obtained in the field in the lab. And then mineralogy is just looking at the soil mineral properties so as to enable us to understand why our soil behaves the way it behaves. Basically, mineralogy is the buildup of every soil. And so with an understanding of the mineralogy of the soil, we are able to know what really influences the chemical processes or the interactions between the cations and the anions and the soil itself. So going to some of the results, like I said, some of the basic classifications just to help us further in our experiments. For example, organic content by 4%. Cation exchange capacity of that soil is this. And so with all of this information, what it basically means is if you have a similar soil on site and you want to compare our results to such conditions, then you have to fall back to some of our material properties to be able to know if those two soils are compatible with our experiments and be able to compare the results. So that's why we did all of this and presented this one. Also, in terms of sorption analysis, some of the methods which we use for sorption analysis, like I mentioned earlier on, is just Langmuir and Frondich isotherm model. And basically, this is just these are basic models that have been generally accepted over time for estimating adsorption and desorption processes in chemical transport or solid transport. And so they just represent different type of soil conditions, and they try to explain the adsorption and desorption processes in the soil, such as, for example, if you have an homogeneous soil or a non-homogeneous soils, these models helps you to predict the interactions because their background or their basis is based on similar soil properties like this. So for the result, we were able to get good data fit to both models. And basically what this says is that our soil has both an homogeneous and non-homogeneous property. So in some zones in the soil, you can have soil with similar properties and surface area. And in other zones, you have soils with dissimilar properties and surface characteristics. And so this is making it quite a complex situation because the soil is going to behave differently across the different layers or zones within the soil. But basically, we can get an average value, which we can use to estimate or depict our results. Yeah, I think we can go to the next page, just to point out there. So this is an example of using our data points and extending using our machine learning. So for example, the graph shows the region of relative concentration, and then the pore volume of the solute that is transported through the soil column. And at the end of the day, we're able to get about 7 pore volume, which took several months to actually achieve based on the flow rate. And then with our machine learning approach, we could predict further up by predicting the behavior within these 6 or 7 pore volumes, and then exponenting that to the other pore volumes that we may encounter in the field. And so you can see that our machine learning approach was able to predict soil property very good at this up to 7 pore volume. And then if we try to mimic the same conditions and go more pore volumes, 7, 8, 9, 10 pore volumes, our machine learning results gives us an idea of what we should expect in terms of the interaction of these cations with the soil.
Sorry, Taiwo, could you actually explain what is a pore volume and what is the y-axis?
Oh, okay. So for the pore volume in the soil, pore volumes basically means the spaces that are available in the soil that are not occupied by the soil grains itself. So that means it is occupied by either air or water. So one pore volume is measured as the volume of the void in the soil. And the y-axis, yeah, in the soil column. And the y-axis in this case, which is the relative concentration, is just the concentration of our solute, which we have diluted, so 1 to 30 or 1 to 90, or the pore volume, or the concentrations that are measured at the outflow of the soil column to the initial concentration that went through the soil column. So initial concentration is C naught, and then the concentration that we measured at the outflow port is C. So this is just a relative concentration that's represented from 0 to 1%. To 1.
So in other words, if nothing is physically or chemically bound in the soil column, then it would come out as 1, right?
Yes, if nothing is bound, that means you have the same concentration as the inflow coming out from the outflow of the soil column. And that should give you a value of 1. So why this is a complex table to digest, I'll just point out the most important thing is that using our substron isotope models to fit our data points, we got very good fit, which is an R correlation value, R square value that shows how well your data fits this model. And we got very good fit to our models, and so makes our data quite reliable for interpretation. And some of the parameters which we obtain that are very important for explaining this results is Qmax. Qmax is the value that is obtained used to measure the concentration or the relative concentration of adsorbed ions on the soil particle surfaces. KL are just sorption, the right word to use, affinity, sorption affinity. And why these are all complex terms, I'll explain what they mean in like the next few slides. So the
Table,
parameters
one
to
thing
be
is you may want to explain R squared equal to 1 means a perfect fit, right? So anything above
yes.
0.8 or 0.9 is close to perfect fit. But I do notice, like for the sodium chloride plus beet juice case, for the sodium cations, the fit is not great.
Yeah. Yes, the
I
fit
mean,
is not great. This is typical for soil experiments. Soil is quite complex and heterogeneous, and so even getting a fit of about 0.76, it's quite good for such a complex system like soil. But then for the rest of the result, we got over 0.8, which is close to 1. So 1 basically means a very good fit with our model and our data set or our result.
perfect fit, 1.0. Yeah.
Yeah. So now, if you look into the parameters that are very important, QM, which I explained the other time, is the maximum adsorption capacity of the soil, which means the maximum adsorbed cation on the soil surface. And so if you use that to explain our result, look at conditions where you have sodium, and then when you introduce beet juice, you could see the differences in the Qmax, which is the adsorption of the cations on these soils. Also, if you look at magnesium cation, you could see the difference when you move from just having a magnesium chloride solution to having a magnesium chloride solution plus beet juice. Now, why this result is very obvious in magnesium chloride, you could also see if you change the scale of this graph, you could see an increase also in the sodium result when you add beet juice to this result. Now, remember I said this Qmax value is maximum adsorption capacity. While in our data set, we're not able to get to that range, we actually use where our data point stop to estimate this result. And one of the things we notice from this is that, one, the beet juice is actually interfering with the absorption or desorption processes of these ions on the soil particle surfaces. So now, when you have beet juice, we believe that the beet juice has its own chemical properties, and these chemical properties are interacting with the soil. And so the cations and the anions from these Deicers solutions are being affected by the presence of that beet juice. And so the presence of adsorption and desorption on the surface of the soil particles are influenced by beet juice addition. Now, we have several ideas which we think, but they need to be further investigated. Is that one, we know from past research by Dr. Shi and his past student that the beet juice contains surface functional groups, and these surface functional groups aids in the adsorption of cations and anions on any surface. And so we think, one, the functional group in this beet juice is actually one, either absorbing these cations within its matrix and then making the desorption and adsorption process much slower. Or two is that this beet juice is coating the surface of the soil particle. And when they coat the surface of the soil particles, they have functional groups that absorb cations and anions to them. And so you have more adsorption of these cations in the soil. But then for our results, what we notice is that the beet juice actually absorbs these cations into itself, and so limits the interactions with the soil. And that translates to a reduction in time for these cations to travel through the soil columns. That means there's reduced interaction between these cations and the soil. And so you have reduced time of transport to get to groundwater. And that raises a lot of concern when you add beet juice to sodium chloride or magnesium chloride in the field, such as the kind of soil that we kind of experimented with. And that is one of the key takeouts from this result, like I would like to point out. So we know that beet juice is advantageous in terms of optimizing adsorption, de-icing operations or anti-icing operation. But this result actually shows that we also need to be very careful how we add beet juice to these brimes, because they influence how these cations interact with the near roadside soils, and they affect the travel time of these cations from the surface to groundwater. The next slide. So this is just basically a continuation of the results. But what we also notice in terms of the anion, which is the chloride ion, is that there is no clear trend in our results. And the differences between the presence of beet juice in this solution is not apparent. Basically, chloride is a conservative ion. It has less interaction with soil, which we also notice in these results. Although for the magnesium chloride, you could see a slight variation in this, but then if you compare that to the cations, you could see a clear distinction between the behavior of chloride and then those cations, sodium and magnesium in the soil. So for this experiment, sodium still maintains the initial postulation that is a very conservative. It does not interact with the soil as much as other cations. And the next result is just showing affinity for absorption. For sodium, we see an increase in the absorption, which is really about 10 times the value of the absorption. Now, this is just an affinity which shows the ability of beet juice to influence the absorption of these cations. So, for example, when you add no beet juice, you can see the KL value is quite low. In fact, you can't read it on the graph. But immediately you introduce beet juice to the surface, you see that affinity to adsorb to the soil particle surface is very apparent. Now, the behavior is not observed for the magnesium chloride. And like we said, there are two conditions which we think are affecting these processes. One is either the beet juice is coating the soil surface, or two, the beet juice is absorbing these cations within its matrix. And this is also like a good starting point for further research to look into these fundamental mechanisms and be able to separate these mechanisms within the soil system. Also, the same sorption affinity. If you look at chloride in sodium chloride, you can see there's no clear evidence of the influence of that on the affinity. But then, although chloride is quite conservative, you could also see that beet juice is also influencing the adsorption processes and desorption processes of chloride in magnesium chloride. Now, to be able to understand the fundamental mechanism of this, we need to isolate each of these conditions in further studies and be able to come up with a clear explanation for that. This is just using adsorption desorption models to get some other soil parameters or very good model parameters to explain our results. The ADE model simply means advection dispersion equations. And basically, these are fundamental equations that helps to explain adsorption and desorption processes in soils under dynamic conditions. So when you have soil solutes or you have salt solutions flowing through a soil, either in a continuous manner or in a pause manner, which is you introduce the solution and then you wait after some time and you introduce in the next stage. Now, these models help to explain some of those interactions. So basically for our experiment, we look into the Ogata and Banks model, which is basically an extension of the advection dispersion equation. Some of the parameters that are very important here is the RD, which is the retardation factor. And what retardation factor means is that how much of the interactions within the soil does how much of those interactions is happening within the soil. So for example, if you have a very high RD value, a retardation factor value, it means that there's a clear adsorption and desorption or adsorption process going on within the soil matrix. And so if you have a low RD value, it means there's no interaction or little interaction between the soil particle surfaces and the salt solutions, cations and anions.
So
on the other hand, is the
sorry, time out. In other words, the higher the retardation factor of the soil column,
the more interaction with the soil.
Yeah, that means the de-ice is gonna move slower, right?
Yes, those cations are going to travel slower through the soil because they interact more with the soil particle surfaces.
Also, do you want to explain the figure on the top right?
So for the figure on the top right is just looking at um, two different conditions. One is once we increase the concentration of our beet juice, remember we started with 23%, but then we diluted to 1 to 30 and 1 to 90. We look at the influence of increasing concentration on the influence of that on retardation factor. And what we notice is once we increase the concentration of this salt solution, you could see the arrow points to the high side of that retardation factor, meaning you expect increased interactions between the soil particle surfaces and the cations of the solute coming in. And then if you look at the beet juice, the other factor, now we introduce beet juice, you can see that the retardation factor, the arrow is pointing to the low side, which is a reduction in the retardation factor. So beet juice actually reduces the interaction between these cations and the soil particle surfaces as observed in our own study. So this is just some of the result from our ADE model, which is the advection dispersion model. And we try to fit with Ogata and Banks model that fits all of our soil parameters. And the figure on the top right side clearly also expands on the previous knowledge. So for example, if you have a coarse grained soil, you should expect a reduced retardation factor, which is less interactions with the soil particle surfaces because now the flow rates, because the pore volumes in the coarse grained soils are larger and the flow rates are higher. And so there's little time for interaction between this solution and the soil particle surfaces. On the other hand, if you have a fine-grained soils with very low permeability, you should expect the flow rate should be lower and increase in retardation, which is increased interaction between the solute cations and anions and the soil particle surfaces. So if you look into the next results, now this is just pointing out those retardation factors. The table on the right-hand side depicts all of the conditions that we observed during our vertical soil column experiment. But the key takeout is that for all of these experiments, we got a breakthrough after 1 pore volume. Breakthrough simply means we got to the initial solution concentration at about 1 pore volume. That is, the inflow concentration and the outflow concentration were equal after about 1 pore volumes. And then we also observed that retardation increased with concentration, which supports the initial postulation. 2 is that we add a decreased retardation with beet juice. Once beet juice is introduced into the system, we notice that the interaction between the particles and the cations and anions in the salt reduce greatly. And that's also reduced the travel time or the travel time of these cations and anions through the soil. And it means that they can reach groundwater faster. For the horizontal soil column, if you recall, we tried to look at different orientations. Now we're looking at the horizontal soil column. The retardation also increased with concentration, except for sodium. And the mechanism for this is not yet fully understood. We need to understand or get further studies on this. But then we still have a decrease in retardation with beet juice. So for both the horizontal and the vertical soil column, introducing beet juice actually reduces the retardation. That is the interaction between the cations and the soil particle surfaces.
Well, maybe
Now,
I'll
if you go,
take it from here. So
okay.
basically, thank you, Taiwo. And basically, what
Yep.
the results mean is introduction. I mean, beet juice into the de-icer products actually changed or altered adsorption of sodium cation and magnesium cation with the soil particles. And retardation to adsorption reduced with the presence of beet juice for both vertical and horizontal conditions. So that means the presence of beet juice as an additive in the chloride salts actually accelerate the migration of those ions through the roadside soil under the investigated conditions. So we mentioned two different mechanisms, possibly. One is the coating of the soil particle surface by the beet juice organic compounds. Basically, they do contain some sort of biopolymer. And the other possible mechanism is the absorption of the cations within the functional groups of the organic material itself. In other words, beet juice can capture some of those cations and prevent them from interacting with the soil, so they migrate through soil faster. So what do we go? I mean, where do we go from here? Certainly, we need a better understanding. So, as researchers always say, additional research is needed. So, in-depth microscopic analysis should be explored to examine these interactions, because that's not the focus of this project. So we didn't go, into the fundamental research. But the experimental data, out of hundreds and hundreds of soil column leachate testing indicate, this trend. So we think additional test or investigation would give a clear picture and better understanding, because we mentioned there are two different kind of possible mechanisms at work. So another thing is, of course, through these soil column tests, we found that salt accumulation after drying increases the surface salinity. That's kind of consistent with our domain knowledge. And also that tends to basically clog up the soil columns and therefore decrease infiltration capacity, as we observed during the experiment. And sodium chloride and magnesium chloride migrate laterally and vertically through roadside soil, with magnesium chloride showing a higher sorption affinity in fine textured soils. So in other words, that's a good thing, because then they're moving slightly slower. And chloride ions, however, move very quickly. They're smaller, they're more mobile and highly soluble. So basically, any retention within the soil is negligible. So they move really fast through the soil columns. And then beet juice additive increases the mobility of sodium and magnesium ions, which honestly is a surprise to us, but the data shows. Why does it matter? First of all, for state DOTs, that means we need to monitor roadside salinity in agricultural zones and make sure, the application of especially these, unconventional deicers, such as the beet juice salt brine blends, is not causing unintentional consequences. And also use organic additives judiciously, because they may accelerate ion migration. Again, for roadside soil, that could mean, if they migrate through the roadside soil faster, they can potentially get to the groundwater faster. And finally, prioritize site-specific testing before any sort of high-volume salt and additive use, especially in sensitive zones. When it comes to translating or converting or transferring lab evidence to field conditions, the real world is really complicated, right? So we need to account for, in the field, the soil heterogeneity and subsurface variability in natural roadside soils. We also need to recognize preferential flow that might be dominant for subsurface transport and cause a deviation from the results we reported here from this lab study. Because when you conduct a lab study, everything is under well-controlled conditions. And in the field, everything is fluctuating, humidity, temperature, or even microbial activity. And also use the results in this study for screening and relative low-risk comparison, but not for prescription, because again, for the site-specific conditions, you need to test that specific soil and take other factors into consideration. Now, yet another one is, in conditions comparable to this study, treat agro-based additives as a potential factor for increased chloride salt ion mobility, as we saw earlier, especially when it comes to sodium and magnesium cations. I should clarify that the original scope wanted to also look into calcium chloride, but it was agreed upon by the project panel after the survey results, like we would focus on these two, which are the most commonly used deicers. Again, the machine learning model, like we mentioned, was helpful in reducing the number of experiments we had to conduct, because otherwise it would be cost prohibitive and really time consuming. But we should employ such methods strictly as an extension tool for lab data. And the one pages, Taiwo, do you want to go over the two of them slightly?
Okay, yes. So all of the results that were presented in the study, we kind of shrink that into a one-pager. And basically, this is just to help transportation and every other audience out there to basically grasp some of the results that we presented and then make informed decisions. So everything we presented is just described briefly in this one pager. And if we start from the top part, what are the potential pathways for chloride salts into roadside soils? And they are basically from runoff of precipitation and snow melt actions. And during plowing activities, you can have these salts being deposited. Also in splash and spray events. Also wind action can contribute to how these solutions migrate from the applied pavement surfaces or the road surfaces to the nearby road soils. And for our results or our experiment, we actually look into two concentrations, which is sodium chloride. And then also for beet juice, we added 20% by weight of sodium chloride solution. And then for the roadside soil that we examined in this study, we basically just look at the clay silt fraction and then the sand fraction are the remaining part of that.
Sorry, Taiwo, there's no need to go into those details, but what I want to clarify is these one pages are not final. We're still going through the panel review. And also because of the way the slide shows, the formatting is a little bit off because the actual slide is in a different size. So, I mean, the actual one pager. And also another point to clarify is there are two of these. This one is focused on sodium chloride. The next one is focused on magnesium chloride because they do behave differently, slightly different, right? Like as we saw earlier. So because when originally we try to combine both into one document, it gets a little bit confusing. So we try to separate them. That's the need. So with that, we welcome your questions.